Okay, I'm going to show you today a Jupyter notebook that I set up to illustrate Terzaghi's one-dimensional consolidation solution. Jupyter notebooks are pretty cool. This is my list of notebooks that I've set up here in my CE 220 material folder. So I'm going to click on the Terzaghi plotting notebook. Now, as it opens, let me just explain what Jupyter does. It allows you to mix rich text with code in these blocks shown here. So this one up here, you can see it's a markdown cell. Okay, what that means is that it's basically HTML. So I've coded up all this stuff in HTML. You can embed latex equations in here. So it's a great way to document what you're doing. And then down here is a code cell. In this case, it's Python code. You can pick a number of different kernels. I'm going to use Python here for this demonstration. All right, so let's dig into the content. We discussed previously Terzaghi's one-dimensional consolidation equation. Here it is. It's a second-order partial differential equation. The solution to the equation is a Fourier series given here, where this u sub z is the depth-dependent consolidation ratio, t is time factor, capital Z is dimensionless depth, Z is depth, and H is the drainage path length. Now you'll notice that the Fourier series requires you to include an infinite number of terms from n equals 1 to infinity to obtain an exact solution for the consolidation ratio. Of course, we can't actually perform the sum from 1 to infinity, so we're stuck with this task of choosing a suitable number of terms in the Fourier series, what I'm calling capital N, to obtain a reasonably accurate solution. It won't be exact, but it will be good enough for engineering purposes. So I've rewritten the equation here. Now u sub z is approximately equal to this truncated Fourier series where we're only going from n equals 1 up to capital N, so a finite number of terms. So how many terms do we need? Well, that's why I set up this code block down here to explore the influence of the number of terms on the accuracy of the solution. Before we get into the code block, I just want to explain one thing about this equation. You'll notice that we have a term here, sine squared of pi n over 2. Well, it turns out that when n is even, the sine squared term is 0. When n is odd, it's 1. So this sine squared term is actually just kind of a filter that says that this expression evaluates to 0 if n is even, and this part evaluates to 1 if it's odd. So from a code writing perspective, we can simplify this equation by removing the sine squared term and then only summing over the odd values of the index counter n. And that's what I've done here. So let's now dive into this code block. I'm going to walk through some of the details of the code. This Jupyter notebook will be available for you to run if you'd like to run it. And so I think it's helpful for me to walk through it so that you understand what all of this is. It's often not easy to understand somebody's code just by looking at it and trying to learn it on your own. Okay, the first line, this percent sign in Jupyter is called a magic. And basically this magic is for matplotlib, which is a Python plotting library that's intended to emulate MATLAB in the way that it plots. And then matplotlib notebook. So I'm telling Jupyter to create the plot within the notebook. That allows it to be interactive. And you'll see I've set up some widgets so that you can change certain values and see immediately how that affects the plot. The next 3 lines are where I'm importing some libraries. So first I'm importing the IPyWidgets as widgets. You'll notice that the py appears in a lot of places. That's for Python. And that's why Jupyter is spelled kind of funny with py instead of pi. And then I'm importing also Numpy. That's the mathematics library that is pretty, you'll have to import this library to do almost anything with numbers in Python. And then I'm importing the matplotlib library. In particular, I'm importing pyplot as plt. So you'll see I'll refer to this plt object and this np object. So I'm importing the library with that as that set of letters. it'll be clear in just a minute. Now, this right here, that little block that I've highlighted, is defining a function called uz. And so let's walk through that. uz is a function of n, that's the number of terms in the Fourier series, capital Z, and t, the time factor. What I do first is initialize a variable u sub z to be 0. Then I introduce a for loop here for lowercase n in range from 1 to capital N plus 1. So the in range means that we're starting at the number 1. We're going to go up until we get to n plus 1, and then the increment is going to be 2. So we're going to go 1, 3, 5, 7, so forth until we get up to n plus 1, and then we're going to stop. This equation right here is just executing this without the sine squared term, right? We don't need the sine squared term anymore because we're only counting the odd numbers here anyway, and that term is always going to be 1 for odd numbers. So you'll find that this equation, it doesn't look as nice as this one, right? This one's rendered in LaTeX. This one is just plain text, but you should find that it's the same. One more thing I'll point out, you see this little np.pi right there. Well, the NumPy mathematics library has a variable called pi. That way you don't have to write 3.141592654 and so forth. Every time you want to use pi, you can just call it from the NumPy library. Same thing here, NumPy has a function called sine. It also has an exponential function that I'm utilizing right there. So that's why I import it as np, because otherwise we would have to write NumPy every time we wanted to execute a function from the library. It just makes it easier to write the code this way. And then after I've done all the summation, I return 1 minus u sub z. So that's the function that does the actual work. The rest of it is just setting up the calculation itself and then the interaction components. So moving on, here's a list that I've created that contains the default time factors that we're going to be using. So 0.01, 0.05, and so forth up to 0.9. This is just the initial value of the time factors. So when we first plot the data, it'll be plotted for those time factors. You'll see that I've also enabled some interaction widgets so that you can go in and modify those time factors just by putting a number in a little text input box. But if you wanted to, you could come in and change these numbers too, and that means that the first instance of the plot will look a little different. It would correspond to updated time factors. Okay, this next command is creating the vector of dimensionless depth values, capital Z. So this is a NumPy function called linspace, and it creates an evenly distributed set of numbers within some range. In this case, the range is 0 to 2, and it's going to create 50 values that are evenly spaced between 0 and 2, including 0 and 2. There's also a log space function that will distribute them evenly in log space, which is pretty nice if we're dealing with variables that we want to plot on a log scale. Now here I'm setting the number of terms in the Fourier series to be 19 by default. That's also a number you can change. You'll be able to play with that. Okay, now right here I'm initializing the plot. So figure comma axes, or fig comma ax, is equal to plt, so that's the matplotlib library, and then subplots 1 1. I'm creating just a single subplot within a plot object, and I'm assigning it to two variables, figure and axes, that we can then modify individually. So here I'm setting the x label to be u sub z. I should explain that the matplotlib library allows you to put LaTeX code in the string declarations for x labels and y labels and titles and things like that. So this is LaTeX code. The $sign opens and closes the LaTeX code. The underscore means subscript, so this will appear as u sub z. Here I'm setting the y label just to be capital Z, and then I'm setting the limits for the axes to be -2 to 1. For the horizontal one, that'll be the degree of consolidation, and then the y limit on the vertical axis is going from 0 to 2. Now we're going to want to make plots for every single one of these time factors. So what I'm doing here is initializing a variable called plots, and then this open bracket, closed bracket just means that it's an array, but right now it's an empty array. So I've declared it as an array. That means that I can perform array operations on it, or list operations on it more correctly, but there's nothing in it yet. So the reason I had to initialize is just so that I can use the append method to add data to the plots list. All right, now here's the function that is actually creating the first plot. So this is the plot that's going to use these particular time factors, 50 intervals on the depth axis and 19 terms in the Fourier series. And so what I'm doing is a for loop. Let me explain how this for loop works, because Python has a kind of a funny structure for for loops compared with other languages like C++. All right, so I'm saying for j comma t in enumerate capital T. All right, this enumerate function will return basically two vectors. One is an index vector. So if this has 11 values in it, it would start at 0 and go to 10. So 11 total numbers in order in their integers. Okay, and then it will also return a vector here, t, that is equal to the values of this capital T list in order. So the j vector will go 0, 1, 2, 3, 4 up to 10. The t vector will go 0.01, 0.05, 0.1, 0.2, and so forth. So that's kind of a nice way to do it. Now we don't have to assign a variable to the time factor. We already have it implicitly in the loop just by doing this enumerate command. Okay, in the next step in the for loop, I'm initializing an array of u values, and these will basically be the pore pressure ratio values that we will want to assign and plot. Then I'm looping over depth, so I have a depth loop embedded inside of a time factor loop. So for each time factor, we're computing values of u sub z at each depth, and that's what we're doing here, u dot append and so forth, and then I plot u and z within the t loop. So I'm basically creating an isochrone that's a plot of pore pressure at a particular time factor, and then plotting it. And as the t loop continues to loop, the plot command will continue to add new lines to the figure. All right, now that's all we would need if we just wanted to make a static figure. But if we want to make it interactive, we need to add quite a bit more code just to facilitate that interaction, and that's what these methods down here are doing. I'll go through these a little bit more quickly. If you're interested, you can find a lot of online help for Python, Jupyter, Matplotlib, and so forth. All right, so this method right here, update t vector, is going to change the value of the time factor that we're using in the plot, and then redraw the plot. So basically this is going to accept a new value of t and the index for the particular isochrone. First I remove the old value of the isochrone, then I insert a new value for the isochrone. Then I create this u vector again, and then compute a new value of the isochrone, and then set the x data, that's the pore pressure ratio data, equal to this new value of u, and then redraw the figure canvas. So this won't regenerate the entire plot, it's only going to regenerate that one isochrone. Makes the code a little bit more efficient. These other, the next two methods are similar to that. This one's updating the depth vector. Okay, it turns out if you change the number of data points in the depth discretization, you have to update all of the isochrones. So now there's two loops in here. We're looping over t and z and doing essentially the same amount of work we did when we created the plot in the first place. The same thing here for the number of terms in the Fourier series. We're looping over big T and big Z, creating u vectors, setting the data to u and z, and then redrawing the canvas. Now we have those methods defined, but we need to also define ways to call those methods so that we do something with them. and that's where widgets come in. So here I'm defining a whole list of widgets. The in widget is a integer slider that allows you to slide back and forth and pick the number of terms in the Fourier series. So the minimum value is 1, the max is 100, the increment is 2, so you'll only be able to select 1, 3, 5, 7, 9, and so forth. And then the value by default is 19. I've given it a null description because I added a label description to it later. And then we have continuous update equals false. So let me explain what this does. If you have continuous update equals true, then when you're moving the slider back and forth, the plot will continuously update depending on the current value of the slider. So if you depress the mouse button, move the slider to the left, the plot will be updating as you move it. It turns out that that interaction was a little bit slow. The plot couldn't really keep up. So continuous update equals false means that it will only update when you release the mouse button. I found that to be a little bit more intuitive anyway, and it works a little better. The NZ widget, that's the number of depth intervals for plotting. Similar thing, it's an integer slider. Continuous update is false. This one goes from 3 to 100 with a step value of 100, or a step of 1 and a default value of 50. And then here I have a whole bunch of T widgets, T1 through T11. Each one of these is a text box where you can put in a floating point number corresponding to a particular isochrone that you'd like to plot. Okay, and then here I'm just doing some styling to those widgets so that they fit in the space that we've allocated to them and they look okay. Here I'm setting the input or the form input parameters. This is just the way that the widgets are laid out on the screen. And then here, these methods are what happens when one of the widgets changes. Okay, so if the change, well, I've defined a method here called change in, and it calls the update in method, which we had up here, right? There it is, update in. We'll go through this sequence of steps here. Okay, so I've defined these methods for changing all of the values that we need to change, and then I've set these observe values for all of the widgets. So this is what's telling the program to actually watch for changes in the widget and then make some sort of a change. So what I'm going to do now is run all here. We'll let the cells run. That figure we were looking at is actually an old instance of the plot that came from before. Okay, and if we scroll down, here we have the plot of all the isochrones. The axes go from -2 to 1, just like we set them to. We have the nice LaTeX formatted label. Here's our z-axis from 0 to 2. This is for double drain conditions. You can see that the isochrones are symmetric about the z equals 1 axis. And then all of our widgets appear down here in this little box. So let's do first the number of points along the depth. So we have 50. These plots look nice and continuous and smooth. That means that 50 really is enough for this particular set of plots. If we were to drag this down to, say, 10, I'll do 12. Now you can see that the edges are a little bit jagged. All of the points are in the exact same spots as they were. It's plotting the exact solution. It's just that it's doing so in a way that doesn't have a whole lot of resolution. So I'm going to put this back to 50 because we want to look at nice continuous plots, not ones that have these jagged edges. Now let's look at these isochrones. Here, this one is 0.01. That's the blue isochrone on the left. You can click it up, 0.02. There, it moved in, right? 0.03, 0.04, and if I do 0.05, it should be right on top of the green one. 0.06, it should move inside, and so forth. Let's put it back to 0.01. I'm going to push enter. If you use the little scroll buttons, it'll update automatically. If you enter a number, you have to push the enter key on the keyboard to get it to update. All right, now let's look at the number of terms in the Fourier series. We're using 19 by default. Let's drag this down to 5 just to see what happens. So what we found is that basically the isochrones over here at high degrees of consolidation, say here at 0.9, 0.8, 0.7, and so forth, those didn't change. They stayed essentially identical, but the one at 0.01 changed quite a bit. Now you can see all these wiggles out here where this was a pretty nice flat line before. So what's going on here? Why does the solution give us this sort of funny, these funny wiggles? Well, it turns out these are erroneous. Those wiggles are not actually part of the solution. The problem is that the number of terms is just not adequate. Let's put this back to 19 just to illustrate a point. Okay, notice how this has a nice curved surface here, and then a pretty straight line surface right there, and then a nice curved surface coming back. Well, the question is, how many sine waves do we need to add together to reasonably replicate this curve? And because it has that flat part in the middle, it takes quite a few sine waves to do that. All right, it takes, well, 19 does a pretty good job. 5, not so great, right? If we go back to 5, sometimes it's a little sluggish for some reason. Well, anyway, there's the solution with 5. You can see those wiggles. That's just because 5 harmonic functions is not enough to get that flat edge. It becomes even worse if we go to lower degrees of consolidation. So let's make this 0.001. And now you can see that this is really pretty jagged. We kind of don't have enough points vertically anymore because this is starting to look like a sawtooth instead of a nice smooth variation. So I'm going to drag the number of points up to 100. May take it just a second to update. Okay, now you can see it's a nice smooth curve right there. So we haven't come very close in this case to the right solution, which would be almost like a box, right? This is coming this way, then there's no consolidation happening in the middle. It's all happening near the ends. If we drag the number of terms up to 99, which is the maximum number I'm allowing in this particular instance of the code, it'll update. There we go. And now it looks nice and boxy, right? Just like we think that the solution should look. Okay, so have fun playing with this. I think you can download it and slide these widgets around, put in time factors, and hopefully learn more about consolidation than you would by looking at a static figure. The key takeaway here is that if you're trying to model consolidation at really low time factors pretty early on in the consolidation process, you're going to need to use more terms in that Fourier series if you're going to model it that way using Terzaghi's one-dimensional consolidation solution. For the higher time factors up here, actually one term does a pretty good job. So you don't need to go crazy summing a whole bunch of terms up in this region, and it's pretty accurate just because it's easy to fit that curve with a single sine wave, right? Just a harmonic function works pretty well.